for tonight. I am the chair of the Science Unwrapped committee, which is it's a huge privilege. This is the last in our series of changes, theme talk for this year. And our speaker tonight is Dr. Susanne Jänecke. And Dr. Jänecke will be speaking on Cache Valley's ancient floods and earthquakes. But we're not ready yet, Susanne, right? This is going to be a multi-part introduction. I'll try to make it as brief and to the point as I can. In addition to my standard thanking the Science Unwrapped committee, and I thank them sincerely, I always like to thank our volunteers because Science Unwrapped is really a two-part event. It's the talk, which is really important, but then it's the volunteer hands-on activities, which is the second part, which is at least as important as the talk. And so a thanks to our volunteers. And I always love to thank people who are volunteering for the first time. And tonight we have quite a few. So we have from the Geosciences Department an activity called Geology Rocks. Get it? Get it? We have, Stokes Nature Center doing an activity on monarch seed bombs. We have Julie Hobbs and Brooke Richards doing a city nature challenge. We have USU Extension doing the Great Salt Lake and water conservation. And finally, we have a group called BioHive, which promotes biotechnology and biotechnological employment opportunities in the state of Utah. So thanks for all those volunteers. I want to circle back to the Science Unwrapped committee, and it turns out that one of our long-standing committee members, Dr. Kim Sullivan, is retiring after at least 10 years of service on the Science Unwrapped committee. And I want to thank Kim and give her a special recognition. Kim, if you want to come down. So in honor, and Kim really is a stalwart of the committee, in honor of all of these 10 years of just really invaluable service. Kim?
Yes.
Thanks a lot, Kim. Thank you. Speaking of the committee, there's another thing I want to announce, and I feel really proud of this. And I feel proud of this not for me, but for the people that help make Science Unwrapped possible. And that is the committee. This is the volunteer groups. This is you. And you don't know what I'm talking about, right? So Science Unwrapped has been recognized by, and this is a mouthful over here, the 2023 USU Committed Community Partner Presidential Award for Community Engagement. So that's a big deal, all right? So we've got an award for engagement in the community engaged learning sphere. And again, this really is an award for the committee, for the volunteer groups, and for all of you in the audience. So thank you to everyone. So I really appreciate that. Thank you. One year leads to another. And so we are changing from our changes theme, and next year's theme will be building on basics. And this is something I'm excited about because it's really simple. And the idea for next year is that all our speakers have to feature some simple principle or small number of scientific principles that tell us a lot about the way the world works. And their talk needs to be structured in ways that address that principle and to illustrate, really starting from the basics, what you can learn about the world as we know it. So I'm really excited about that series for next year. I hope you are too, for building on basics. Now, for Susanne, let me introduce Susanne, our speaker for tonight. So Susanne Jänecke is a geoscientist. You called yourself a mapper, but I've turned that into a map maker, but somebody who goes out and maps things and then makes maps from them, and a field geologist who specializes in mountain building, active fault zones, you hear about all that tonight, and basins of Western North America, another thing you'll hear about tonight. Susanne is recently retired from the Geosciences Department, a full professor, now is an emeritus, and we're happy to have Susanne here tonight. Suzanne's Bachelor's of Science was from the University of Michigan in geology, but interestingly, in anthropology as well. Susanne got a master's degree from the University of Arizona in geology. and a PhD from the University of Utah in geology. Okay, Susanne loves geology. She really does, and I know that it's a fact. And in fact, Susanne is a fellow in the American Geological Society, which is a very prestigious honor. A bit of background. Susanne was born in Germany. Her parents migrated with her family to Michigan in 1965. She grew up in Michigan and gradually worked her way west through a series of employment opportunities and in schooling. Susanne loves art, gardening, landscaping, and I'd also venture to say walking, because our paths have crossed more than once out on various walks. And I tend to be looking up and around, and Suzanne's eyes tend to be focused down on the soil to look at geological features. Geology runs deep in Suzanne's family. She told me that her paternal grandparents, both of them, were geologists. She didn't know this until relatively recently that her grandmother was a geologist. And I'm a geneticist, and I don't think this is genetics, but it's a little spooky. Her husband, who is here, Jim Evans, is a geologist. Her daughter is a geologist. And I think it must be contagious, right? So I like geology. I want to keep my distance tonight, just in case I say a biologist. Okay. Susanne says that Cache Valley geology is so world-class that she's been researching it since she's moved to Utah, and you'll hear about Cache Valley geology tonight. In her talk, once again, Cache Valley's ancient floods and earthquakes. So, Susanne, please.
Okay, thank you very much. I'm so excited to be able to tell you about the world-class geology that we have around us, and I'm really pleased to be part of this series talking about change, because it turns out that here in Cache Valley and 2 valleys north of us, there's been a tremendous amount of change that's occurred in relatively recent times. So before I charge into the talk, I want to do a quick little tutorial about faults. I'm going to talk about faults at the end of the talk, and we're going to use these models here to simulate what Cache Valley looks like. And to understand what a fault is, oops. Oh. There we go. There's a crack on the left and a crack on the right, and a fault is one that's had motion across it. So any crack in a rock that's had motion is a fault. So one of these is just a crack, and one of these is actually a fault. Which one? Kids only, please. Which one is the fault? One on the right. Excellent. Okay, so we have started building Cache Valley already with our model here. And in the model, I'm going to make 2 faults. I'm going to take out a little bit in the middle, and so we now have a first draft of our model of Cache Valley, and we are now ready to start talking about all the interesting changes that have occurred here. And so I think the title of the talk might best be to say we're talking about recent changes around us. We'll talk about floods and earthquakes and volcanoes. And we're going to talk about work that I've been fortunate to do with a number of colleagues and students over the years. And we'll look specifically in the area north of us. We'll start in Gem Valley. Oops, excuse me. Still getting used to the pointer here. Whoops. Where did we go? I need to go back. I'm sorry. This is less intuitive than it looks. Sorry. Okay, there we are. That's where I need to be. Okay, so we are in Cache Valley, and we're at the end of the white arrow. The white arrow is going to show our location in all the following slides. And it might come up a little bit later, so those of you who are good at map reading might be able to find our location before the arrow comes up. So challenge yourself to see if you can locate us near the L in Logan right here in Cache Valley. So we'll talk about Cache Valley. And we'll also go north and talk about Gem Valley and Marsh Valley. So these three valleys have really interesting geology in them. And I'll show maps similar to this multiple times. So let me introduce you to some of the basics here. The faults are white. Actually, you know what? We need a little bit more darkness. Could we darken the room a little bit? Can you see the white faults on the map? Not really. They seem a little washed out to me too. So the Wasatch Fault is the westernmost one. And then there's two in Cache Valley. There's the West Cache Fault at the base of the Wellsville Mountains, which runs about right here. And then the East Cache Fault is at the base of the Bear River Range, okay? So they have logical names. And every area that's a little bit bluish is where Lake Bonneville flooded when Lake Bonneville was here. And I bet many of you have heard about Lake Bonneville. We have beautiful shorelines around us from Lake Bonneville. So we'll learn about that. We're also going to learn about the Bear River, and it's going to be this blue wavy line. And the mountains will be kind of rough and brownish, sometimes gray, okay, in the figures as we go through. Okay, so to us, it feels like this is a very static, permanent situation, that our mountains over here and the valley that we're in is not really changing that much, but it has actually changed a lot for us geologists. This has been a really busy place, and a lot of different things have happened here. Many things in the last 50,000 to 100,000 years. And if we took a time machine back, even 5 million years ago, the mountains west of us might not be here. So this is a really active area from a geologic point of view. And things are happening, like the East Cache Fault that you see exposed here has had 2 big earthquakes since Lake Bonneville was in this area. Okay, so some things that have happened on what feels like a geologic instant are the rerouting of the Bear River. And we'll talk about that first. We're going to start up in Gem Valley. Then we're going to move south and talk about Lake Bonneville filling up the area and then flooding out in the Bonneville flood at the north end of our valley. So we'll go into North Cache Valley. And then these are almost instantaneous geologic processes. And then we are going to move back close to where we are, to this region here, to Central Cache Valley, and we'll talk about how the valley was created, that the rivers flow through and that the lakes filled up in one earthquake at a time. So we created the valley, Cache Valley, that we're in, one earthquake at a time by having displacement about 2 meters, which is about this much, during a major earthquake at a time on the East Cache Fault, east of us, and the West Cache Fault, west of us. Okay, I'll get a hang of this pointer. It's kind of weird. Okay, so why do we have earthquakes here? Well, we are an earthquake country because we are part of a very broad plate boundary between the Pacific Plate and North America. And we're more in North America than the Pacific Plate, and you would think we'd be entirely in North America because most of the motion is concentrated here on the San Andreas Fault Zone, but every red fault in this map here is taking up just a little bit of extra displacement between North America and the Pacific Plate. And these are all active faults, which means that they can have big earthquakes in the future, okay? Any red fault could produce an earthquake, and this is pretty unusual that a plate boundary is this wide. This is 4 states wide, 150 kilometers or so. Has anybody spotted where we are in Logan? Did anybody locate us before my arrow? I bet some of you did, yeah, very good. Okay, so because we're in the plate boundary, there have been earthquakes through this area. And if we plot up all the earthquakes since about 1950, we get a map that looks like this. And notice the outline of Utah here. We're going to notice the outline where Wyoming and Idaho, Utah come together a little bit east of Bear Lake. We'll notice that in a lot of the maps. So look for that triple junction. And our location is right there, right in the middle of a pretty dense alignment of earthquakes, which is called the intermontane seismic belt. So we have a higher than typical risk of major earthquakes here. Okay, so we'll talk about that. So what has happened here is that these earthquakes occur on faults. They cause slip, and one earthquake at a time, they produce the basin and range province that we're in, with the basin being Cache Valley, the ranges being the Bear River Range and the Wellsville Range, and we see that on the map here. We have a whole series of mountains and valleys going across this area. The other thing that's happening here is that the hotspot, the supervolcano under Yellowstone National Park, is broadly responsible for a lot of volcanic activity throughout this region. And each of these orange triangles represents an area where some of that is occurring. And you'll notice that right here at the northern end of where the Bear River turns around and heads back into the Great Salt Lake, there's a lot of volcanoes. And that's because those volcanoes interacted with the river and caused the Bear River to shift from its original course. It used to flow into the Snake and past Pocatello and go across Gem Valley. So we'll investigate that big change that occurred. Okay, locate ourselves. Okay, so starting up in Gem Valley, here's the Bear River again. At the northern tip here in Gem Valley, it's been known for quite a while that the Bear River used to go across Gem Valley, flow past Lava Hot Springs, up past Pocatello. And we know this because basalts would flow down the river almost to the outskirts of Pocatello. We have examples of that 430,000 years ago. A pair of basalts did that. And there are a number of volcanic centers and a lot of volcanic rocks in Gem Valley, like the ones that you see in the photo here at the bottom, that started to erupt in this area about 2 million years ago. And we didn't have a whole lot of age determinations and didn't know details of which volcano was where and exactly how this all interacted with the river. So we were interested in trying to sort that out. And so my student Brady Utley, who you see here, and I and colleagues, we worked on trying to sort out this interaction between the river and the volcanoes. And just to take a quick peek at the volcanic rocks there, they're often covered in dust, so they're a little bit hard to see, but here's the throat of a volcano. If you get into a cinder cone, it might look like this. And here we're seeing the Bear River flowing through the rocks that are in that area, which are primarily basalt. And basalt is a type of volcanic rock that's pretty heavy, dense, dark, and it flows. It's very fluid when it comes out, and it flows into the lowest area that's around. Okay, so Gem Valley is really weird. Have any of you noticed this when you're up there? There's very strange things about Gem Valley. And one of them is that the surface is very rough, and that's because there's so much basalt everywhere. So here's my pocket basalt. If I put that on the valley floor everywhere, we're going to get a really rough surface of the valley floor. Whereas Cache Valley is much smoother than that because we have sediments there. There's 3 low volcanoes that have grown here. Do you see this pile of volcanic rocks in the middle? That's one volcano. They're so low that you almost don't notice them. But we've been able to separate out 3 separate volcanoes here. So I'll take that off. Whoops. Back. Yeah, can you see the piles of lavas are making 3 volcanoes here? And there are cinder cones and craters that these lavas are erupting out of, and then they flow laterally away from the central part of each of those volcanoes into low-lying areas. And we sometimes end up with a finger-like basalt flow or a ribbon of basalt. And there's one that's quite interesting in this area here that we're going to take a closer look at. That particular ribbon of basalt, I thought might be the basalt flow that pushed the Bear River into its current modern course. So we sampled that and we took a look at that ribbon of basalt and tried to see what we could figure out, and we noticed on Google Earth, can you trace the pattern of it? Goes up and down and up and down. It's kind of wiggly, and it has a loopy pattern. This has a shape that to a geologist is really diagnostic of a meandering river. Rivers have this loopy meandering pattern. I'll draw it in for you. And so this seems to be a place where a basalt flow went into the Bear River and has the same shape as the Bear River did. So to make sure that this is a basalt that flowed in the Bear River, we need to match up the shapes. Is the size and shape of this loopy pattern, is that similar to what we see on the Bear River nearby? So it's a little washed out, but hopefully you can see that we have very similar sizes and shapes of the meanders. So this does look like it was a part of the Bear River when that basalt flowed in there. So we were a little disappointed when we dated this basalt. It turned out to be much older than the basalt that actually finally pushed the Bear River into its modern course, but it did provide some really interesting information. We were able to find out that 170,000 years ago, the Bear River was flowing across along the yellow line. We could reconstruct this and see that the diversion of the Bear River must have been occurring right near the northern tip of the Bear River Range at this spot called SP. I'm really sorry about this pointer. This is just impossible to use. I had not realized this would be such a steep learning curve. And we see cinder cones around here. We have various eruptive centers, and that is the place where we must have had a diversion occurring. And one of these green cinder cones and one of these eruptive centers, these are the places where we suspect the lava flow came from that pushed the Bear River from its original course going to the Pacific to its new course. And that change occurred about 50 or 60,000 years ago based on evidence from lakes to the south. And I was hoping to be able to tell you a brand new date on this basalt flow, but age determinations always take a little longer than we hope, so I'll have to give you an update later on when we find out how old that is. Okay, so the Alexander volcano is the one that pushed the Bear River around by basically time over time erupting up through the bed of the Bear River, and eventually it became big enough and a lava flow went right down into the channel and caused this massive diversion, which has allowed billions of dollars of extra economic input in Utah. Imagine if we didn't have a Bear River, we might not have a Great Salt Lake. So this single basalt shield volcano has done a tremendous amount for us here in Utah. Okay, now we're going to shift to Cache Valley and look at the northern end of Cache Valley where the outlet of Lake Bonneville was. And because the Bear River has been shifted into this basin and now flows through Cache Valley, there's extra water available during glacial times so that the lakes that form at that time are rising higher. Lake Bonneville, the last of these lakes, was higher than any of the prior ones. And as a result, it flowed out and overtopped its rim, and the green Bonneville River carried any excess water that was in that lake out to the Pacific Ocean as well. So we're going to explore that. Let's look at Lake Bonneville. It covered most of western Utah. It's a huge lake, had a very big impact, and it occurred because, we would think because it was during glacial times. You would think it formed because of melting ice. But in fact, the climate was different. The glaciers were farther away. The climate was different enough. It was cooler, more clouds. There was a lot less evaporation, a little bit more rain, and that's why we produced this enormous lake that was up to 1,000 feet deep in places. And then in southern Idaho, the Bonneville River carried the excess water off to the Pacific. So another way to look at Lake Bonneville is to look at a plot that shows time, old on the left to today is right here, and the elevation of the lake. We would be sitting right in that spot. The elevation of the lake, it started to rise about 30,000 years ago, and gradually it rose up and overtopped at the north end of Cache Valley, and this Bonneville River started to form. And it was only active for a few thousand years, which for us geologists seems like a teeny tiny little bit of time. It's a very short phenomenon. It wasn't there all that long. And in the middle of it, the Bonneville flood occurred, and we dropped down roughly to the elevation that we're at here now. So if we took a time machine and we all went back to 20,000 years ago in this auditorium, what would happen? We drown, exactly. Yes, we would drown. You're reading the chart really well. Excellent job. Thank you. Okay, well, thankfully we didn't do that. Okay, when Lake Bonneville rose up, it overflowed at the north end of the valley, and we produced this Bonneville River, the green line flowing peacefully out of the lake. And you can think of the Bonneville River as coming out from the edge of a bathtub. So the lake filled in this area that's in the purple color or the blue color, and we had a situation that was pretty stable until some centuries later. We don't really know why, but for some reason, the Bonneville flood started, and we had a very drastic change. And all of a sudden, you started to cause this huge erosion event, and a massive flood occurred starting right here in Cache Valley at the northern end, and that happened about 18,000 years ago, okay? And it started at the tip of the arrow there, and it cut a big red slice across the geologic dam, which is the two mountain ranges close to each other. A big slice was carved by the flood through that area. And how long do you think the flood would have lasted? Does anyone have a guess? So keep it in your mind. Think about how long that flood might have lasted. And all the water from the rest of Lake Bonneville had to make its way into Cache Valley so that 100 meters of the top of Lake Bonneville could be emptied out of the north end of the valley. So this was a really dramatic phenomenon that occurred. Okay. I'm sorry?
How long did it take?
I'll tell you in a little bit. In a little bit. Think about it some more. All right, and what did it look like when the flood rushed across the landscape? Well, we scoured some. Did I skip something here? I did skip something. Oh, no, wait a minute. I am really, really sorry about this pointer. I did not realize it would be this hard. Okay, the flood ripped out across southern Idaho, and it ripped up big chunks of basalt, like this one, 200 miles away. Okay, 200 miles away, we had huge chunks of basalt that were ripped up. Do you see all these big boulders in the background that were carried? They knocked into each other, got polished up and rounded in the process of being carried by the flood. So we had a really powerful process going on, and it changed the landscape dramatically. And when we look at the route of the flood, it was the same route that the Bonneville River took, and all of these yellow areas are places where there's either big scours that have occurred, where the water was funneled into a relatively narrow area, or when it spread out, then you would drop the giant boulders that had been ripped off of the walls of the Snake River Canyon across southern Idaho. So the boulder field that I was showing you is at Hagerman, right about here. So a very large distance away from where the flood started, but the water was still rushing at such a high, powerful speed that these enormous boulders were being carried across the landscape. And this is what the flood might have looked like. This is a simulation showing the flood. It's actually the Missoula flood, which was also a mega flood. Very similar landscape in Washington where that flood occurred to the one in southern Idaho. And careful analysis suggests that the flood was only, did you get it, 15 to 30 days long. This is amazing that it was so quick. 15 to 30 days long for the upper 100 meters, 350 feet or so of water from that giant lake across most of Utah to rush out the north end of our valley. It's just incredible to imagine what that might have looked like. And there's an RV for scale in case you missed it. This is a really fun video to Google. You might want to watch it afterwards on your own. It's really pretty cool to see what happened there. Okay, so after the flood happened, we had a big slot cut, this orange slot cut through the geologic dam that was there, and we see the aftermath of the flood. And so we can now see where the new outlet of Lake Bonneville is. The original outlet is that green line at the top of the image. The new outlet is the white one in the northeast corner of Round Valley. This is what was said by a famous geologist 130 years ago. But when we look down in the valley from the mountains, from the top of the Bannock Range right here, looking down into Round Valley 20 years ago or so, I saw something like this. And I'm wondering if you can see it. It's a little washed out, but do you see the loops there? Does this remind anybody of anything? Not eskers, but eskers are related to meanders, rivers. This looks like another meander system. And counting them up, they're really big. 1, 2, there's 5 visible, there's 7 or 8 of them total, and they're very large meanders in a place that basically is just a marsh now. There's a bird refuge there, and when we look at big meanders, we need to know a few things about rivers and meanders. So here's a side tutorial. Do you see these meanders on the river here? We can tell very quickly that the biggest river has the widest channel and the largest meander loops. So the biggest meander loops are the main channel. So clearly, this Alabama River that we're looking at is a much bigger river than the tributaries coming in from the side. See how tiny the channels are, and the loops are much closer together. They're a different scale. So we can quickly tell that the biggest river is the one from the upper right to the lower left. Okay? So when we look in Round Valley, we can see these meanders looping back and forth. These are over 2 kilometers apart. The wavelength from one loop to the next loop is more than 2 kilometers, and this used to flow to the north. We have tributaries coming in from the side that are all merging northward and connecting into this scour that was slotted, up into the natural dam at the north end of the valley. Okay. And so let's compare these meanders with the Bear River. The biggest river around us is the Bear River, okay? And the Bear River, we see the little loops in the lower right. How do you think that there's a match? So we have little wiggles on the Bear River and big wiggles on the meanders in Round Valley. So there's a terrible match. They don't match very well at all. They're not the same size. So let's look at the whole Bear River and see how that matches. So the Bear River starts in the lower right in the Uinta Mountains, and you see tiny little meanders. And they get bigger and bigger as more water comes in, and they get bigger. And by the time you reach the Great Salt Lake in the lower left-hand corner, those are the biggest meanders on the Bear River. Are any of those the size of the green meanders in? That's right, they're not even close. Not even close. Okay, so what does that mean? So where did all that water come from? Anyone have an idea? Yes. Lake Bonneville, yes. Excellent. You should be a geoscientist. It's so fun. Yes, the only possible place that all that water could come from is Lake Bonneville. So we were looking, this green wiggle that we found there in Round Valley was an unknown piece of the Bonneville River that exists up there, and now we're not getting, there we go. So what does this mean? Where could all the water come from? It had to be from, it's not advancing. Okay, there we go. Yeah, Lake Bonneville is the only possible source for all that water. And that means that the outlet of Lake Bonneville shifted far south into Cache Valley, roughly to the little town of Clifton. Some of you may know where that is, from its first outlet that was actually in Marsh Valley. It started north of Red Rock Pass, and then it shifted all the way south to Clifton by the time that the Bonneville River just barely ended its overflow of Lake Bonneville. So that was really an interesting discovery. I just happened to be wandering around in the mountains up there, and I saw that. Okay, let's move on to our final topic. And our final topic is going to be forming the valley around us, one earthquake at a time. And when I was flying back from the East Coast, I got to see our first snowstorm. Little did I know we were going to have so many of them. And you recognize what we're seeing here? The valley floor is pretty flat, but the deepest part I outlined, the wetlands, the Cutler Marsh is here, the Little Bear River is right there, and the Valley View Highway is that white line going across. And you can see the really straight edges of the mountains. The East Cache Fault is on the left side. The West Cache Fault is on the right side, okay? And where is, what kind of a pattern do we think we're seeing here based on the location of the deepest valley and the rivers and the marshes and so on? Well, let's look from overhead. I made this map to show the deepest part of the valley is this dark bluish black area. And you know, do you see it's scooched over on the west side of the valley, just as I saw from the airplane, and it's right next to the West Cache Fault Zone. Okay, and there we are. So I want you to help me make the block model for this part of the valley. We're going to take the basalt out because there's no basalt in Cache Valley. And for now, I'm going to remove the Bear River. So do you think, is this a good way for the model to look? Do we have a flat valley floor, do you think? Yes, no, yes, no, no, no. Okay. What if I try, let me see. What if I do this? I'm going to tilt the valley floor towards, I think my label is here, towards the Bear River Range and the East Cache Fault. And if you put some water in here, that water would all run over to this side. What do you think? Is this any good? No, 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 no. That's right. It's wrong. And flat wasn't right either. But how about now? What do you think? Is that right? Yes. Oh, you're so smart. That's right. We have evidence here that the valley is tilted to the west. I was really surprised to discover this because the biggest, baddest fault around here is the East Cache Fault. But it turns out that, anyway, this is the correct interpretation. So hopefully we got, which one is the right one? Which model was the best one? West tilt, the middle one. The middle one's the right answer. Very good, and you helped me figure that out. Thank you. Okay, so what does that mean? Well, it means that the West Cache Fault has recently been especially active. So the West Cache Fault is right next to the marshes, the lowest part of the valley. And it means that in the last 10,000 years or so, since Lake Bonneville was here, this part of the West Cache Fault has had more earthquakes on it than the East Cache Fault over at the base of the Bear River Range. I'm scratching my head about that. Wow. And then we had these earthquakes. Did any of you feel the earthquakes that happened near Benson in January? Yes. Yes. Okay, those earthquakes, do any of you live in Benson? Did you? Trenton, oh yeah, I bet you felt them. Okay, those earthquakes all map out right here in this red polygon. They happened in the West Cache Fault Zone. So I said, yay! You know, my ideas about the West Cache Fault Zone being seismically active, they might be right. That was pretty cool, because little earthquakes like that don't hurt anybody, right? That's good news. Okay, so the valley's been dropped down, the mountains have come up, and we've had westward tilting like we're seeing in our block model, because geologically recently, the West Cache Fault Zone has been more active than the East Cache Fault Zone. And I didn't really have time to put this in here, but it seems like they take turns. The East Cache Fault is sometimes more active, then the West Cache Fault is more active, and then they switch back and forth, and our valley might be like a teeter-totter. Okay, yes, you have a question.
Would that be described as the fleet that we're on going ping-ponging back forth between the two?
It's not ping-ponging would be sideways, right? But it's the tilt direction has shifted. It was definitely eastward, and now it's westward. And it seems like it's gone back and forth more than once or twice, but that's harder to prove. But yes, we have this very interesting pattern that may be occurring here. And this means that also that our valley is being created one earthquake at a time as the valley drops down about 2 meters per big earthquake. Okay? All right, I'm going to wrap up with a little bit of information about earthquake hazards, which might be more for mom and dad than for the kiddos, but actually everybody needs to know about earthquake hazards, right? This is an important thing because we are in earthquake country. And it turns out that when you look at all the evidence that we have, there's a major earthquake in Cache Valley every 2,000 to 3,000 years, okay, which is not that often. Mostly they've been on the West Cache Fault Zone in the last 10,000 years. So if I had to make a bet, I would predict that our next major earthquake might be on the West Cache Fault Zone, but it could be on the East Cache Fault Zone too. You know, they both still could potentially produce big earthquakes. The place that is the most dangerous and most likely to produce a big earthquake is the Wasatch Fault. And it produces its central part that I made the big fat red line there. That part has a major earthquake every few hundred years. Between 200, 300, 350 years or so, there's a major earthquake somewhere on the Wasatch Fault. Okay? When was the last one? We're overdue in both cases. When was the last one in Cache Valley? 3,800 years ago, plus or minus. And what's the size of these earthquakes? There have been earthquakes of the high 6s to low 7s in Cache Valley and on the Wasatch Fault. And that's what we expect to happen again in the future. We're predicting high 6s and low 7s. And when you look at the historic earthquakes, I plotted the ones that have occurred near us. There are 3 here. They're not anywhere near the same size. Even though the numbers look similar, there's a lot less energy in the historic earthquakes that we've had. So we really haven't had any of the big ones, of the major earthquakes that we're expecting in Utah. We haven't seen those historically. Okay, and the greatest risk is on the central Wasatch Fault, from Honeyville down to south of Nephi. Okay, so what might happen during a future big earthquake? Unfortunately, something like this might happen if you are in an old brick building. So unreinforced masonry buildings, ones that were completed before 1970, are the most dangerous and most likely to collapse. And these are examples of damage from these relatively milder earthquakes that we had in Utah. Magna, the Richmond earthquake in the lower left, and then Elsinore in central Utah is what we're seeing. So any building that was completed after 1970, and most single-family homes are pretty safe, unless they're brick and were completed before 1970. So what should you do? It starts shaking, drop, cover, and go under the table, okay? And several of you should join me under there, and we wait until the shaking stops. And then we go outside. Don't run outside. That's what most people do, but that's not what you should do unless you are in one of those unsafe buildings. Okay? So it's important to learn about this beforehand, make a plan, think about where you work, where you live, and Google shakeout exercise. There's really great information about earthquakes and preparedness on the web. This is a great place to find that information. So drop, cover, and hold on, unless you're in an old brick building, okay? Okay, We made it. What did we learn? What did we learn? Well, this is an amazing place that we live in. There's great geology that's happened here. A lot of changes, and the Bear River has been pushed around by a volcano, and that volcano is called Alexander. And we should thank Alexander for bringing all this extra water into Utah, because that is a very important thing for our state. Lake Bonneville used our valley to fill up, overflow, and start the world-famous Bonneville flood, which is the largest flood that we know of on the face of the earth. That's a pretty amazing thing, and it's all started right here in Cache Valley. And then the next major earthquake in Cache Valley might occur on the West Cache Fault Zone. It's turning out to be a more active, more important fault zone than many of us realized, and that's been an interesting thing to learn about. Okay, so I'm done. Thank you very much for your attention.
Okay, here's what we'll do too, is if we can talk into the box, all right? So these are catch box mic. How good is your catch? About as good as my throw?
Yeah. I think my mic is on, is that correct? Yeah. Cool.
So the Great Flood you're talking about, was that the one that also formed the Badlands? The Badlands?
Which Badlands?
Oh, the ones in Dakota?
No.
Oh.
No, our flood, the Bonneville flood, roared across southern Idaho, and it's expressed mostly along the Snake River channel between Pocatello and Hell's Canyon, so west of Boise. Can go to the map. It's all the area that was yellow in the map of the bigger picture. There we go. So this, oh, no, don't tell me it's not working either. Ah, there we go. This whole area here is where the flood has the most impressive evidence is preserved there. And so field trips, if you want to go look at melon gravels, just Google field trip to see melon gravels. There's great videos about it, and you just want to see some of these in person, because they're these giant boulders that are all rounded and polished and just sitting out in these fields like some crazy thing happened, and of course it did. Yeah.
Okay, another question.
Really great talk. Was there some event that caused the lake to critically overflow and drastic? Was an earthquake or some event, or was it just gradually eroding and then suddenly gave way? What caused the flood?
Oh, that's a great question, and we don't really know. There's many possibilities. I'm on record as suggesting that an earthquake might have triggered the flood. But it's also possible that the overflowing lake just eventually eroded back, kind of like Niagara Falls is eroding back, and you just eventually caused the failure of that natural dam. And it could have been nothing more exciting than erosion that initiated the flood. And unfortunately, the record is destroyed. So all of the landscapes we'd like to study to figure out how the flood started, those are all gone. And we're having to reconstruct what was there. That makes it hard for anyone to prove their hypothesis or my preferred hypothesis. It's just an idea. Thank you.
Hi, thank you, Suzanne. So while all this excitement was happening in northern Utah and in Idaho, what was going on in southern Utah?
Well, the lake actually almost reaches into southern Utah. Let's see. Oh, here's the map. I cut it off before the very southern end. The severe desert was part of the Great Salt Lake. Oh, it's in the top corner. Okay, thank you. There were no pluvial lakes in the extreme southern part of Utah, so they missed the action. I don't know.
Kind of boring.
Yeah, maybe boring. That's right. Yeah, if we wanted to do an exciting time machine tour, we would not go to southern Utah at that time. But there were volcanoes erupting there actually at the time. There's plenty of exciting geology everywhere, actually. Yeah. Jim reminded me. The Santa Clara volcano is 40,000 years old. That's the youngest one. It's a little bit older than Lake Bonneville was. Yes,
So are these maps that you see wherever on the internet that have like all of Utah covered in this giant lake, is that just completely made up fantasies?
No, that's actually fairly correct. So almost the entire Basin and Range province west of the Wasatch Mountains was covered by Lake Bonneville, and the lake had, at its highest level, it had the shape that we're seeing in the lower right, but it was only up at that highest level for a few thousand years, and Mr. Lake Bonneville thinks it was only up there for a geologic instant. He thinks that as soon as you overtopped at the north end of the valley that the flood started. And many of us geologists are skeptical because we see such tremendous shorelines cut into the edge of our valley, every other valley around, really steep wave-cut cliffs that I don't think could have formed in a geologic instant. You need maybe centuries, maybe 1,000 years to produce the big cliffs like at Point of the Mountains. Do any of you go airplaning or whatever, just skydiving over there? There's really high, steep wave-cut cliffs that are 300 meters high there. And I don't think you could make those in a geologic instant. So there is a lake over most of western Utah. That is correct, Lake Bonneville.
Okay, big toss. Ready?
All right, hello. How do you prove things in geology? Because you talk about proving your hypotheses, and like you can't like recreate these things. So what does proving things look like?
Well, you test the alternatives as best as you can. And you know, it's actually, I love geology because it's a little creative like medicine, you know? You don't have you can't do all the tests. You can't redo the geologic history of the earth. You have to take what evidence is preserved and try to put together the best story you can and figure out, like we're trying to test whether a particular basalt near Soda Point diverted the Bear River. We've collected a sample of it, we're dating it, and if it comes out to be the age that other evidence suggests the diversion occurred, that would be consistent with the hypothesis. But if it's a lot older, then we got the wrong basalt again. As we thought the meandering basalt that I showed you, we were convinced, oh, this is the basalt that pushed the Bear River around. Well, it tried, but failed. There was still that westward course after that based on lakes in southern Gem Valley that couldn't have been there if the Bear River had already been diverted.
Very cool.
So
Thank
it's
you.
a complicated thing, but it's fun.
You made it hard.
Yeah.
Okay.
Okay, so the Wellsvilles are such a tall range, and you know the low point is below those, and yet when you're up on top of the Wellsvilles, there's a lot of evidence of former marine life up there. So did the Wellsvilles eventually rise through the lake or through the Lake Bonneville, or were they always taller? How did that happen?
So those marine fossils that you observed, they're good for you for noticing them. Those are very old. They are hundreds of millions of years old, mostly Paleozoic in age. Oh, yes, so Jim reminded me, geologic time scale. If we make all of Earth history my arm, 1 meter long from my spine to my fingertips, the Paleozoic would be here from there to there. And the time period I was just talking about is like my skinniest little fingernail. So we were discussing the ice ages and the last 10,000 years, and on that time scale, it's just a tiny little bit of time. And the fossils that you've been observing would be here in my hand, probably Mississippian, Pennsylvanian fossils from long, long ago that were brought up by faulting between the Wasatch Fault to the west and the West Cache Fault Zone. I actually have a cross-section in here. I put a few extra slides in just in case I got excellent questions like yours, so that I could answer these questions. There we go. So the top of the Wellsvilles, okay, right there, are Pennsylvanian and Mississippian rocks. Those are 450 million years old or so, and they were brought up on the West Cache Fault, which started about 4 or 5 million years ago, and the Wasatch Fault on the west side, it may be as old as 10 or 12 million years old. So they've been brought up between those two normal faults.
Okay, we'll make this the last question, and actually Kim Hageman is a Science Unwrapped speaker from not that long ago.
Yeah, would you explain how the basin and range were formed and also what time period on your arm that was formed?
Yeah, the basin and range is forming in this very broad plate boundary between the Pacific and North America. And I'll go back to the beginning. There we go. The basin and range is pulling apart roughly east-west. And part of the reason that it's extending is probably because it had been pushed together so much in the past when we had subduction of many plates under North America. It thickened the crust, which when you stop the subduction and strike slip motion, relative motion like the San Andreas Fault, took over, the crust was too thick to maintain itself, so it started to spread laterally. And that's part of the whole plate boundary of the Pacific Plate in North America. But why the basin range is still extending is actually a hard question for us geologists to completely answer. There's many causes of it. And you wanted to know when it started. Okay, it started about 55 million years ago in Canada and about 35 million years ago in central Nevada. And it was older in the south. It sort of migrates around. It has multiple phases of extension. It's a complicated beast. So I can't give you a short and quick answer.
That's fine, thank you.
Okay, I want to thank Dr. Jänecke.
Thank you, everyone.
And I want to thank everybody here for what is a transitional and I think a really strong year for Science Unwrapped. I cheated and turned around and took a few photos to look at the crowd. I love the turnout. I thank you for being here, and I hope that you're here next year for our next Science Unwrapped series. So thanks very much, and please go out and enjoy the activities.
Yeah.